we're going to go a little back again to 10.3. And this is looking at matrices and systems of equations. So it's a little different than the matrices we were looking at, because the matrices that we were using, they didn't represent an equation. They're just, a matrix it's just an array, a rectangular array of entries. Now a matrix isn't necessarily have to do with equations. Now each entry has a value, but due to the fact of how systems of equations are solved, using matrix notation works out really well, right? So that's why we call what we're going to be, even though we're doing matrices, it's going to be called an augmented matrix. So an augmented matrix takes only the coefficients of the systems of equations. Now, what is a system of equation? That's the example that we're going to look at here. That it has multiple equations. Now you can have a system of 2 equations, 3 equations, 4 equations, and of 2 variables, 3 variables, 4 variables. We're going to be looking at systems with 3 variables involved. Now, this is a little bit of a review from maybe like intermediate algebra, where you learned about system of equations. Mainly, you probably worked with just 2 variables, and then you had different methods of solving those. Some people call it the substitution method, which was to isolate a variable and plug it into the opposite equation to try to isolate and solve and get a value for one of your variables. Then you had the addition/elimination method, where you would add equations together to eliminate variables to be able to isolate one and find its value. And that's the method we're going to use in this particular section, which is the addition/elimination method. Now that's what we used. That's the term that was used in algebra. To solve this system, we're going to use something known as elementary row operations. Because since we are going to change this system of equations into a matrix, remember, matrices are made up of rows and columns. So we're changing the verbiage a little bit. Now, like I said, we're using the method of the addition/elimination method. So that's why something that elementary row operations allows us to do is that we can add rows to one another. That's the addition portion. Because as we're adding, the goal is to eliminate one of our variables. But the process of eliminating, for numbers or terms to eliminate, they need to have the same value with an opposite sign, right? 4 and 4 and -4 will cancel each other out, right? If we're going to be adding them, 4 plus 4 is not going to cancel, but 4 plus -4, that will eliminate. So that's why we have this multiplying a row by a non-zero constant. And the idea is, it's an equation, so as long as we multiply to both sides of the equation, it is balanced. We're not changing the value of the equation, but we are trying to get it to have a similar value to the variable that you want to eliminate with from the other equation. And sometimes you can also interchange your rows. For example, if you want things to be a little bit easier, sometimes you'd rather change row 1 to be row 3 or row 2 to be row 1. For whatever reason, it might have a nicer number to eliminate. I normally don't use this option too much. I really just stick to the first 2. So this is what I use. Right? These are the operations I use to help me get to my solution. But there's a particular format to help me solve, because I can't just eliminate one variable. Remember the rule of thumb that we talked about. The number of unknown variables is the number of equations you need. We have 3 unknown variables, hence we have 3 equations. But there has to be a particular format, right? To get to this format, we use elementary row operations. What does the format look like? Well, there's a name for it, and it's known as the row echelon form. Now, row echelon form says when all its non-zero rows have a pivot. Now, the pivot has to do with, and it says right here, a pivot is just a non-zero entry. Right? So that non-zero entry such that all the entries to its left and below are equal to 0. So the very first, when you go into a row, you want to make sure there is a number. Well, the first number you run into that's not 0, you want to make sure everything below it and to the left of it is 0. Next row, right? This is our very first non-zero number, and everything to the left and below is 0. And then the next one, everything to the left and below is 0. I'm not worried about what's above and to the right. Now, there is something known as a reduced row echelon form that extends this definition to wanting everything above and to the right to be 0, and then your diagonal to be 1s. I don't do it all the way there just because you're going to notice to solve some of these problems, it's really tedious. It's a lot of addition, subtraction, and multiplication. And when it comes to doing a lot of addition, subtraction, and multiplication, there's a lot of room for minor errors. So you want to be careful, make sure you're showing all your work, because with these problems, it is really easy to make a very small mistake. You could drop a negative, you could add instead of subtract, and that's going to change the whole entire process. So, to sum this up really quick, we need to get this system first. We're going to convert it to an augmented matrix, and I'll show you with an example what that looks like. Once it's an augmented matrix, my goal is to get it into row echelon form. To get it to row echelon form, I use my elementary row operations. That's how these all work with one another. Now, this GEM stands for, because this whole process of writing it as an augmented matrix, trying to get into row echelon form using elementary row operations, is known as the Gaussian elimination method. That Gauss is a mathematician that developed this form of solving a system, and that was his process of solving this system, was write it as an augmented matrix, get into row echelon form by using elementary row operations. So without further ado, let's do this example. So like I said, an augmented matrix, again, it kind of has that rectangular box, right, that we were seeing before. But this pertains to an equation. So I'm going to look at this equation and I'm going to use all the coefficients. And you want to make sure, sometimes some books might change the order of the x and the y and the z to make sure that you're not doing just something like a robot, and you're keeping track of that everything is corresponding properly, right? So my first column, I'm just using the coefficient 4, 3, -2. Make sure you use the sign that's according to it. 8, 8, +1, -4, right? Because it's -4z, so I'm going to include the negative there. 5, 12, 4, -11, and -17. Now, the idea is to get into row echelon form. So what does that mean? I need to get everything below this so I go to the first row, and the very first number is not a 0. So that means I want to get everything below this number into 0 to the left and below, but there's nothing to the left, right? That's the idea. So with all its non-zero rows have a pivot, so that's that non-zero entry, such that all the entries to its left and below are equal to 0. So that means I need to get these two numbers to equal 0. But I can only add two equations at a time. So I'm going to start with trying to get this value to be 0. Now, like I said, we're going to add these equations together. We're going to add them together right here and have everything written out. Oh, and something to keep note. So a little difference between the matrix and augmented matrix is this dashed line to sort of represent and separate where your equation is. If you have to, once you have to go back into the system notation, you'll know where your x, y, z, and your equation and value are, where everything will be. So, how do I eliminate this, right? That's where we use elementary row operations. So I'm going to start by knowing that if I want this to be 0, that tells me I need to change my second row. So I'm no longer going to have this exact same row. And I need to add this with my first row to give me my new, this is going to be the new row 2. Because this is going to be different, because if I need this to be 0, that's going to impact all these other values in that row. But I want to focus on how can 4 and 3 eliminate each other. Well, one, I need these numbers to be exactly the same. So I'm going to take row 2, multiply by 4. I'm going to take row 1 and multiply by -3. It's almost like finding the LCD or LCM. You're just trying to find the, what can I multiply, right? Because that's one of my elementary row operations, is to multiply a row by a non-zero constant. Because if I multiply by 0, it's going to defeat the whole purpose and cancel everything out. Now, I like to write it just because it helps me keep track of the work I'm doing. And then I write it out in the very next rows. So I start by writing that first row. So 4, multiply 4 to the entire second row. So it's going to be 12, right? 4 times 3 is 12. And then 4 times 8 is 32. 5 times 4 is 20. 4 times -11 is -44. Now I'm going to do -3 times 12 is going to give me -12. And then 8 times -3 is going to give me -24. And then -4 times -3 is going to give me +12. And then 4 times -3 is going to give me -12. And then if you notice, that first term is going to become 0. And that's what I was looking for. But then doing this does change every other value. Now remember, this is I'm not changing my first row. This is my new second row. And that's what I'm going to copy into this new matrix. Sometimes I like to update it. So my first row is still the same, right? -4, 4. But then I input my new row 2. Just to keep track that I'm doing everything. It might be a little extra step, but it does help keep track of things. But now I need this bottom one to be, to become a 0. The nice thing is, 1, it's already negative. And then the other thing, 4 and 2 are multiples of each other. All I need to do is multiply this third row by 2, and that would already eliminate row 1. So let's write this. Let me just put this up here so it splits it. So I'm going to multiply 2 to row 3, and I'm going to add it with row 1 to give me a new row 3. I'm just going to put an arrow. That's what I'm looking for. So, remember, we're going to add them together. So 2 times negative 2 is going to be negative 4. 2 times 1 is 2. 2 times 12 is 24. 2 times negative 17 is negative 34. And then I just have to write the entire first row because I'm not multiplying anything. But when I add, I get exactly what I'm looking for. That very first entry becomes 0, 10, 20, negative 30. Now I can update that in my new row 3, which would be 0, 10, 20, negative 30. So that was the first row. Remember I said you want to make sure the very first pivot, everything below it, so meaning the first non-zero entry, which here is 4, everything below it and to the left is 0. So now, check. So now let's move to my second row. That first pivot, I need everything below and to the left to be 0. So this is already 0, but I need to get rid of that 10. Now this is where you have to be careful. Because if you notice, in both of these scenarios, I used the first row to help me cancel everything in that first column. But I'm trying to eliminate something in my third row, second column. So here I need to use the second row to help me eliminate an entry in the second column. Because if I use the first row, the problem would be I could get rid of this 10, but this 4 will eventually add with this 0, and it's going to change its value, which I don't want to do that. But here, anything that I multiply, if I multiply each row by a value, 0 isn't changing. And once I add them together, 0 plus 0 is still going to give me 0. So I know for sure, I can already say that these two values here in this first column will stay 0. But what do we need to do? Because this is 8 and that's 10. So what would I need to multiply by? Well, I know first things first, or what probably comes to mind first is multiply 8 by 10 and then 10 by 8. But there's another number they both share before you start making these numbers really, really, really large. I would actually take row 3, because if you notice, for me to change this number, that means this entire row is going to change again. So I need a new row 3. And I also know that another number they share, I can just multiply row 3 by 4 plus, and then multiply row 2 by negative 5, and that's going to give me my new row 3. So we're going to add these together. So multiplying 4 to row 3, I just write that out. That's 0, 40, 80, and negative 120. And then I just write my second row times negative 5. 0, negative 5 times 8 is negative 40. 32 times negative 5 is going to give me negative 160. And then negative 56 times negative 5 gives me positive 280. Now here, you see how they cancel each other out. That first column is still 0. Now my second column is 0. And then 180 minus 160 is negative 180. And then 120 plus 280 is positive 160. So the second row is still, the first row is still, I never got a new row 1. That always stays the same. And then I have my row 2. I didn't manipulate it this time. I used it to manipulate the third row a second time. And now it is 0, negative 80, and positive 160. Now, you don't have to do this next step, but you can if you want. And that is to take this equation and put it back into its augmented form, which now that would be 4x plus 8y minus 4z equal to 4. But then that x is 0 now, so I'm just going to have 8y plus 32z equals negative 56. And then the x and y are 0 here. This is going to be 80z equal to 160. And hopefully you can see that I can take this last row, 80z, because that's one equation, one unknown, that I can just divide both sides by negative 80. And that leaves me with z is equal to negative 2. And now if you look at your second row, I have, since I know z, I can take my second row, which is 8y plus 32 times, and I can plug in negative 2 that I got for my z. And that should equal negative 56, right? That's going to give us 8y is negative 64 equal to negative 56. And for the sake of some space, right, we'll add, of course, we'll add 64 to both sides, right? I'll just write it here, small. That leaves me with 8y is equal to 8, which I divide 8 to both sides. I'm going to get y to equal 1. And now that we know both z, we know both y and z, we can try to find x. And that's going to give us 4x plus 8 times 1, because y is 1, minus 4 times negative 2 equals 4. That's going to give me 4x. Now 8 times 1 is 1. Negative 4 times negative 2 is going to give me positive 8. 8 plus 8 is going to give me 16 is equal to 4. I'm going to subtract 16 to both sides. That leaves me with 4x is equal to negative 12. Hence, x dividing 4 to both sides is going to give me x is equal to negative 3. And this process here, this is known as, let me make a quick note. This is known as back substitution, because we wrote everything back into a system of equation. I solved for one of my variables, I plugged it into my next equation, and then my next one. And this is an ordered pair in 3 dimensions. So the solution to this system is -3, 1, and -2. That's the ordered pair solution. Now we can do one more example real quick. Move a little faster. But again, we have 1, 1, 3, -1, 2, -1, 3, -2, 5, 4, 10, 14. Now, it is super nice when this first row has a 1, because remember, I can multiply 1 to anything, and it would stay exactly, it will become whatever I multiply it by. So, luckily, the first row and second row, that first column, the value is already the same. All I need to multiply is -1 to row 1, and that's going to give me my new row 2. So what does that look like? So let me write row 2 first. 1, 2, -2, 10. Multiply -1 will be -1, +1, -3, -4. And I just add them together, which would, adding these will give me, the first ones would be 0, 3, -5, and then 6. Remember, this is my new row 2. And now, again, to get rid of this 3, all I need to do is multiply the first row by -3. So I'm going to take row 3, add it with -3 times row 1, will give me my new row 3, which row 3 is 3, -1, 5, 14, plus multiply -3 will give me -3, +3, -9, and -12. Adding this together, once again these cancel. 0, 2, -4, +2. And if you want, you can skip this step, but it keeps me organized. I update all my new rows. But this is why I said you want to be careful and make sure you write everything and double check all your work. Not just to get full credit, but to make sure you're doing everything correctly. Now I just need to eliminate this next 0, this next third row, second column entry. And I'm going to do that by multiplying row 3 by 3 and multiplying -2 to row 2 to give me my new row 3. So that's going to be row 3 times 3 is going to be 0, 6, -12, and 6. Write that here. Write that again. 0, 6, -12, and 6. Multiplying -2 to row 2 is going to give 0, -6, +10, and -12. We add all these together. Sometimes this acts up. We get 0, 0, -2, and then -6. Again, if you want to rewrite it again, you can. I mean, if you time this is really only taking a couple of seconds. But what you do want to be careful with is make sure you update it with the new equation. You don't want to accidentally be copying the wrong one. Now this next step, again, is also up to you, right? You can start the back substitution if you like, but you can also write x minus y plus 3z is equal to 4, and then 3y minus 5z is equal to 6, and negative 2z is equal to negative 6. And this is where we can do our back substitution, because I'll take negative 2z equals negative 6. Divide both sides by negative 2. Z is going to equal positive 3. I take my second equation, which is 3y minus 5 times 3, because that's what z is equal to. That's going to be 3y minus 15 equal to 6. We're going to add 15 to both sides. It's going to leave me with 3y is equal to 21. Dividing both sides by 3. Y is equal to 7. I should probably move this so it's just not too full. And then last but not least, we have x minus 7 plus 3 times 3 equals 4. That's going to be 3 times 3 is 9, plus negative 7 is going to be x plus 2 is equal to 4. We're going to subtract 2 to both sides. X is going to equal positive 2. And there is my solution. So x is 2. Y is 7. And z is 3. And there's my answers. And there we go. That's what I would be looking for. There are two scenarios. This is just the scenario 1 solution. It's only what I'm going to be focusing on. When you get an infinite amount of solutions, is that as you're doing all these cancellations, you end up with an entire row that's just 0. When there's no solution, you end up with a row that has zeros. But remember, since this is a system, it would then be equal to some number that it's not actually equal to, meaning you won't be able to back substitute because you would get to something that does not exist, because a 0 will cancel out z, which would be 0 is equal to some number that's not 0. But I'm mainly focusing on actually doing all this work to get to an actual solution for the system. So keep trying these and see what you get.